Okay, let's dive into this. Welcome to another explainer where we take, those really complex, intimidating concepts and just break them down together into crystal clear, manageable steps. Today, we're tackling an absolute mathematical magic trick, mathematical induction. It's basically the bridge between simple, everyday arithmetic and the mind-bending concept of infinity. If you've ever stared at a math problem and thought, wait, how could anyone possibly know this works for literally every number ever? Well, we're going to figure that exact thing out today.
I mean, really think about this for a second. How do you prove an equation works for infinity? If I hand you a math formula and say, hey, this works for every single whole number in existence, how on earth do you test that? You can't just plug in a 1 and then a 2 and then a 3 and just keep going forever. You'd literally be calculating until the end of time. And guess what? You still wouldn't be finished because infinity isn't just a really big number, right? It's endless. So mathematicians needed a loophole. They needed a clever, logical shortcut to prove something works forever without having to actually sit there and do the math forever.
And that brings us to the specific beast we're taming today, the sum of cubes theorem. It looks a little scary, but let's translate this math into plain English. Imagine you're playing with literal building blocks. You have one block, then you build a bigger cube made of 8 blocks, then a really big one of 27 blocks. The left side of this equation is just you adding up those cubes forever. 1 cubed plus 2 cubed plus 3 cubed, all the way up to some random number we'll call n cubed. Now the right side is this neat, compact little formula, n times n plus 1 divided by 2, the whole thing squared. This theorem is boldly claiming that no matter how many millions of cubes you add up, that short little formula on the right will always give you the exact same answer. But again, how do we prove it works for every single number without testing them all?
Well, we use mathematical induction. Let's think about this using a really simple, everyday analogy. Imagine an infinitely long line of dominoes stretching out way past the horizon. You want to prove that every single domino is going to fall down. Now, you definitely don't need to walk down the line and push every single one yourself. You actually only need to prove 2 things. First, that you can push over the very first domino. And second, that the dominoes are spaced perfectly so that if any one domino falls, it will absolutely, guaranteed, knock over the one right next to it. If you have those 2 rules locked in, boom, the whole infinite line goes down.
So, to keep us perfectly on track, here's our daily schedule for this explainer. First, knocking the first domino. Second, the inductive assumption. Third, the heavy lifting algebra. And finally, a final exam review table.
All right, let's jump straight into chunk number 1, knocking the first domino.
So we're basically testing this for the number 1. That is our very first domino. If we split the equation, looking at just the left side, 1 cubed is, well, it's simply 1. Now let's check the right side formula. Plugging in the number 1 for n gives us 1 times 2, which is 2. Divide that by 2, you get 1. And 1 squared is 1. Since both sides equal 1, the equation is perfectly balanced. The base step is proven. We just successfully pushed over the very first domino. Okay, before we get back into the weeds, let's just quickly zoom out. What we're looking at here is the universal pattern of basically every single induction question and answer. It's a 3-step dance. Step 1, prove it works for the start, which is usually n equals 1. Step 2, assume it works for some random spot in the middle. We'll call that n equals k. And step 3, prove it works for the very next spot in line, k plus 1. Master this 3-step pattern, and I promise you can solve any induction problem.
That brings us to our second chunk, the inductive assumption.
Now, what's really interesting about this slide is how we move from the physical proof of number 1 straight into the abstract realm. We transition into this next phase by basically just swapping out the letter n for the letter k. Listen closely, because this is where a lot of people mess up. Let me highlight a really frequent error students make right here. They often think they have to somehow prove this step. You absolutely do not. This is purely hypothetical. We're simply saying, hey, let's just assume our formula works perfectly for some random domino way down the line, which we'll call domino k. So we write out the exact same formula, but we replace every n with a k. We're essentially just packing this assumed truth into our toolbox because, trust me, we're going to absolutely need it to build our final step.
And here we go, the climax of the explainer, part 3, the heavy lifting algebra.
All right, so here is where we write out that massive string of cubes again, but this time we're going past k cubed and adding the very next term in the line, k plus 1 cubed. On the right side of the equation, we take our assumed formula and carefully plug in k plus 1 everywhere there used to be a k.
Now, the goal here is brilliantly simple. We just need to mathematically manipulate the left side until it perfectly, exactly matches the right side.
But warning, stop right here for a second. This is the number one trap. Don't fall into the algebra trap. Notice that huge section of the left side? The 1 cubed plus 2 cubed, all the way up to k cubed? We already have a shortcut for that. Remember, in our previous step, we assumed that huge string of numbers equals our neat little formula. We absolutely must substitute our assumed formula into this new, bigger equation. If you forget to do this and try to do algebra on an infinitely growing string of numbers, you're going to have a bad time. It'll fail every time.
So once you safely substitute that shortcut in, it basically just becomes a game of algebra. We take our substituted fraction and add it to the leftover k plus 1 cubed term. First things first, we find a common denominator. Now, time for a quick pop quiz. Do we expand all these big terms out, or do we look for something to factor? The answer is factor. For sure, factor. Expanding all of this will trap you in an absolute nightmare of algebra. Instead, if you look closely, notice that both pieces share a k plus 1 squared. By pulling that out to the very front, the messy remaining bits consolidate together perfectly.
So the crucial point is, after factoring, the algebra just elegantly collapses. It neatly ends up being k plus 1 squared times k plus 2 squared all over 4. And guess what? This is the exact perfect match to the right-hand side of our setup. We did it! We algebraically proved that if the k domino falls, the k plus 1 domino has absolutely no choice but to fall down too.
And this brilliantly illustrates our final piece of the puzzle, Part 4, the final exam review table.
Okay, here is your ultimate final exam review table. Take a mental snapshot of this. It chunks out the entire complex proof we just did into a simple, reliable study pattern. When you see an induction problem on a test, just breathe and follow this chart. Base step, your goal is n equals 1. Your method is simple arithmetic. Assumption, your goal is setting up n equals k. Inductive step, your goal is proving n equals k plus 1 by substituting your hypothesis, finding a common denominator, and factoring. Stick to this game plan, and you literally will not get lost.
To wrap up today's explainer, I want to leave you with a completely fascinating thought. Mathematical induction shows us that we don't actually need infinite time to solve an infinite problem, right? We just need a flawlessly logical pattern. If we can prove a formula works forever just by checking the very first step and then the logical connection between the steps, what other infinite problems in logic or computer science or heck, even in life, can we solve simply by zooming in and just looking at the very next domino? Keep pushing those dominoes, keep exploring, and I'll see you in the next explainer.